In this module, you will learn about construction and working of an electric motor. An electric motor converts electrical energy into mechanical energy using the magnetic effect of electricity. You find electric motors in household appliances such as fans, refrigerators, washing machines, pool pumps, and flow vacuums. An electric motor is built on the principle that a current-carrying coil rotates when kept in a strong magnetic field as it experiences torque. An electric motor consists of 6 main parts. An armature that consists of laminated sheets of soft iron through which passes a shaft. A coil in the form of an insulated copper wire looped over the armature. A magnet that produces a strong and uniform magnetic field. A commutator, which is a metal ring split into 2, and is also referred to as split rings. This commutator is connected to the 2 ends of the coil. The shaft passes through the center of the commutator. 2 carbon brushes fixed to the 2 split rings, connecting them electrically to the coil. A battery that provides electrical energy to the motor. Let's examine how an electric motor works. Consider a rectangular coil PQRS, placed horizontally between the north and south poles of a magnet and connected to a battery. The end of PQ part of the coil is connected to the battery through the split ring S1 and the brush B1. The end of RS part of the coil is connected to the battery through the split ring S2 and the brush B2. Initially, current is directed from P to Q in the arm PQ and from R to S in the arm RS. This arrangement is similar to that of a current-carrying conductor in a magnetic field. According to Fleming's left-hand rule, the force on PQ acts in a downward direction and on RS in an upward direction, forming a couple. The couple acting is maximum at this position. The coil begins to rotate until its plane becomes vertical. That is, perpendicular to the direction of the magnetic field. Magnetic fields of the coil and the magnets become parallel to each other as the coil rotates by 90 degrees and the couple acting on the coil becomes 0. However, the coil continues to rotate further due to inertia. When the coil rotates by more than 90 degrees, the split rings also rotate along with the coil. Now, the split ring S1 connects the end PQ of the coil to carbon brush B2. Similarly, S2 connects RS to B1. This reverses the current through the coil. The current now enters the coil through S2, passes along S, R, Q, P and leaves the coil through S1. The torque acting on the coil causes PQ to go up and RS to go down. A torque acts on the coil whenever the split rings are in contact with either of the brushes. The torque is maximum when the plane of the coil is parallel to the magnetic field and is zero when it is perpendicular. On completing one full rotation, the split ring S1 connects PQ once again to carbon brush B1. Similarly, S2 connects RS to B2. Thus, as long as the coil is connected to a battery, it continues to rotate and convert electrical energy into mechanical energy. The power of an electric motor depends on the strength of the current through the coil, the number of turns in the coil, the area of cross-section of the coil, the strength of the magnetic field, and the lamination of the iron core. This lamination reduces energy losses. This brings you to the end of this module. In this module, you learned that an electric motor converts electrical energy into mechanical energy using the magnetic effect of electricity.